Hi, I thought I'd show you one of the more interesting aspects of electronics design, and I'm sure I've done this many times before, but I was going to go through it again, so why not? Hey, turn on the screen recorder and go through the process of choosing a particular chip for a design. In this particular case, a particular op-amp for a hypothetical improved microcurrent design. Ta-da! There it is, the µCurrent. This is actually a really old design. Dates back from, I believe it was 2008. I had it published in Silicon Chip in April 2009. It dates back to 2008, so it's more than 12 years old now. And this new gold version I did in Kickstarter in 2014. So that's over 6 years old. So anyway, I thought it'd be interesting to have a look at the current state of op-amps, and in particular low offset chopper op-amps. What is the best op-amp on the market? Because in the µCurrent, you should know I've done quite a few videos on this over the years. I use the Maxim Max 4239 or the 4238. They just got different bandwidth variants. And I actually cascade two of them in series to get increased bandwidth, and I've done a video on that. And here it is. I'll link it in somewhere up there and at the end and down below if you haven't seen it, because it is rather fascinating how you can actually cascade or put in series op-amps like this to increase the bandwidth. So just a brief overview of that. All op-amps have what's called a gain bandwidth product, where the bandwidth of the op-amp will actually decrease when you increase the gain. So in the case of the µCurrent, we need a times 100 gain, and if it's got a bandwidth gain bandwidth product of, let's say, 1 megahertz, then you have to actually divide that one. If you have times 100, you have to divide that 1 megahertz bandwidth by 100, and that's the effective bandwidth of the op-amp. So it's not much fun when your whiz-bang 1 megahertz op-amp actually suddenly has a bandwidth of 10 megahertz when you need a times 100 gain, which is what we need in the µCurrent. Of course, it's designed for measuring small voltage drops across a sense resistor and overcoming burden voltage on a multimeter. But most people these days use it for like low current measurement. That was never the original intended purpose, really. I just included the nanoamp range just because I could, really. So anyway, the more you cascade in series like this, the more you're actually going to get an improvement. But you can't just put infinite number in series and get infinite power and get your 1 megahertz bandwidth. There are diminishing improvements here. So yeah, look, by the time you get like 3 in series, the improvement is only 1.25 times, as opposed to just adding a full stage. Adding 2 stages, you get like 6.4 times improvement in the bandwidth, based just by putting, times 10 and times 10 instead of times 100. Anyway, there's the formula up the top there for those playing along at home. So yeah, that's an interesting video. So what I wanted to do is actually have a look at what the current state of the art is, because I haven't looked for many years now. I mean, back when I was looking, pretty much the Max 4239, 4238 was pretty much the duck's guts in terms of op-amps, because pretty much there's one major criteria. Well, there's 2 major criterias. The first one is the offset voltage of the op-amp, because when you're measuring low currents like this, you don't want the offset voltage of your op-amp to like have a residual offset on your multimeter that you're using to measure the output. Sure, you could null your multimeter, null it out and things like that, but it's not. If it's nice if it's actually trimmed and calibrated, or in this particular case we don't trim and calibrate. We actually I actually use like this 10 milliohm resistor in here, for example, is like a $4 resistor. It's really expensive because it's 0.1% 10 milliohms, and these are 0.05%, so we don't have to trim anything, and we use pretty much, well, what was at the time practically the lowest offset voltage op-amp on the market. So it had 0.1 microvolts, a typical offset, as we'll go into, and that changes a little bit when you cascade them in series like this. But yeah, anyway, so pretty much the µCurrent, the good thing about it, and the reason why it's relatively expensive for the type of parts in here, is because these parts used in it are quite expensive, so that you don't have to do any calibration trimming or anything like that. So yeah, we're going to do a video just looking around the market for op-amps. Try and find the best. In this particular case, it's a chopper amplifier. I won't go into like that's how they get the low offset voltages. It chops at a certain frequency. In the case of the Max 4239, it's about 15 odd kilohertz or something. So there's a little pole response in there of so it has disadvantages. But chopper amps give you extremely low offset current, almost negligible, but yeah, let's take a look. Is there anything better these days than the Max 4239? I don't know, haven't looked. So that's why I'm going to do this video. A lot of people say this is one of the most boring aspects of electronics design. I disagree. I think it's one of the most exciting aspects because it's like looking up something on Wikipedia. Like you go look up, a couple of minutes, look up something on Wikipedia, and before you know it, you go down the Wikipedia link rabbit hole and you're learning quantum theory and, I don't know, goat farming or something. And the same thing can happen with chips here. When you start browsing, doing parametric search and stuff like that, you often find very unusual parts. You go, oh, wow, I didn't know that part existed. Whoa, and then your brain starts thinking and you get another idea and then you get sidetracked. Oh, I got a new project idea, and then you forget that project idea and go on. Anyway, yeah, it's one of the most exciting aspects of electronics design, in my humble opinion. Let's go. Just a quick design explanation why we need a low offset voltage here. In this particular case, like in the order of 0.1 microvolts nominal, which is what the Max 4239 has, is because, well, that sounds like bugger all. Like what's wrong with even 100 microvolts or something like that? Well, the thing is, the gain, you've got a total gain times 10 for a times 100 gain here. So any input offset voltage on the effectively, here's your input. If you have 0.1 microvolts typical offset voltage here, you multiply that by 100, and eventually you're going to get out of here a typical offset voltage of 10 microvolts. And, well, once again, that doesn't sound like a lot either, but think in terms of your typical 4.5 digit or 50,000 count multimeter on your millivolt range, which you might be using to actually measure the output of this thing, or you might be using some data logger output, or, whatever it is, then that 10 microvolts is 0.01 millivolts, and that's the least significant digit of a typical 500 millivolt range on, say, a 50,000 count multimeter. So you want the offset voltage to be, basically the least significant digit of your measurement device. So we're targeting that nominal 0.1 microvolts offset voltage. So we're looking for anything better than that. If there's nothing better than that on the market, or maybe we can get something that's the same, but it might be cheaper, for example. So there might be benefits, or it might be higher bandwidth. Because I said, didn't finish my thought before, there were two design requirements. One is the offset voltage, two is the bandwidth. And this one, we increase the bandwidth. What is the bandwidth in microcurrent? I forget, it's like 300 kilohertz or something like that. So if we could push that to 500 or even a meg, whoa, now we're talking. Right, so we got the Max 4239. This is the latest datasheet, I believe. Anyway, here we go. DC performance, ideal for high precision sensor interfaces, blah, blah, blah. 0.1 microvolts, typical. Well, they don't say typical, it just says ultra low 0.1 microvolts. Never believe the banner specs, always go in. They're actually very nice here, and they tell you 2 microvolts maximum at 25 degrees C. But I've done extensive testing on these chips over the years, and if we go further in datasheet, we might see some bin-in data. A good datasheet will have bin-in data for an important, basically one of the main benefits of this chip, because it's a chopper amplifier, is they call it they don't call it chopper amplifier up here, but that's the technique it uses to get your ultra low offset voltage. So anyway, yeah, so it could be as much as 2 microvolts at 25 degrees C. I mean, you're not going to use this thing at 85 degrees C to minus 40. So, you take your 2 microvolts worst case, but I've done extensive testing over the years, and it is pretty much in the order of 0.1 microvolts, 0.2, something like that. It is real, that is quite typical. So anyway, the 4239 has 6.5 megahertz gain bandwidth product, which is pretty schmick. So we need, if we're looking for a better chip, we might get, we might even want to trade off. You might even want to, this is where you can come a gutser, by the way, when you're designing a product, you rigidly set your specifications. I must have this. And that's it. I draw the line right there, and I must have this bandwidth and this offset voltage. If you aren't willing to negotiate in there, then you either might not be able to find a chip, or you might use a really expensive, you might be pushed into a really expensive solution that prices your product out of the market, for example, or it's just, all sorts of things can do that. So you might want to go, oh, I found this chip, but it's got, 0.2 microvolts typical, but its bandwidth is like 20 megahertz or something. You might want to go, bandwidth, yeah, I think I'll live with the higher offset voltage on my product if it means I get a much higher gain bandwidth or total bandwidth of my product. So you just be willing to negotiate in your specs when you're searching for parts. Pro tip. And this one is up to 5.5 volt supply voltage. A larger supply voltage might be an advantage here because of dynamic range. Dynamic range is very important for a product like this that you're trying to measure. If your product's switching from an amp down to 1 microamp and it's switching like that, that's a massive dynamic range, and that's why you need multiple ranges. So, but if you've got a higher voltage supply for your op amp, then you can actually get a higher output voltage, a higher dynamic range for a given range resistor, for example. So, I won't go, I've probably done it in other videos, I won't go into the examples, but an advantage would be a higher supply voltage. If you run at 12 volts, find one that goes to 12 volts, for example, woo! But then again, if it's going if the output's going into the input of a data logger or like an ADC or something like that, then you might not care about that higher voltage. There's no advantage. You just have to live with the multiple ranges and lower dynamic range and stuff like that. And then there's noise specs as well. This is 1.5 microvolts peak to peak from DC to 10 hertz. So that's like only 10 hertz. That's just the low end stuff. You've got to look at the higher end stuff. Anyway, so there's lots of specs that go into this, and a drift as well, 10 nanovolts per degree C drift. So if you're measuring things, generally if you're using a product like this, you'll generally use in the lab. You're not going to be using it in the field. So it's not going to, temperature's not going to change that much. So generally you don't have to care about that sort of thing. But if you were designing, say, an outdoor product that could go from being used indoors and then being used outdoors, and I had this problem when I worked on seismic equipment that was used on the back of seismic survey vessels during testing on the back deck of the boat, for example, in the middle of the ocean. It could get like 50 degrees, like baking hot on the back of this on the back deck of the ship. And then when they throw it in the freezing cold water, huge temperature variations, like 40 degrees temperature variations between actually testing and then deploying your product. And temperature drift was a big thing. Anyway, as I said, don't believe the Banno specs, 0.1 microvolts. Always go have a look. And here it is, typical 0.1, maximum 2 microvolts. But it really gets nowhere. Note 1, always read the notes. Oh, come on. Note 1, guaranteed by design. Thermocouple and leakage effects preclude measurement of this parameter during production testing. And they just went, oh, bugger, this is too hard to measure in production. We just guarantee it by design. But there's nothing wrong with that, of course. It's fine. Because the reason a lot of these parts, precision parts, are expensive is because they're expensive and time-consuming to test. It's really difficult, especially really precision stuff, low leakage and low offset voltage and stuff like that. Really difficult to measure on a mass scale when you're designing production test jigs. So yeah, that's why you can pay $5-10 for a real precision op amp, for example. It's like, why? It's the same amount of silicon. Yeah, it's the labor and the complexity that goes into testing and guaranteeing the performance. Anyway, they are screened, blah, blah, blah. Okay, let's go. Now, I told you they might have some binning. Ta-da, here it is, down here. Input offset distribution. Not all manufacturers will give you this. Maxim's being pretty generous here in giving. Well, look, they've measured. Do they say how many parts? They don't say. Oh, it might say it up the top. No, doesn't say how many parts. Yeah. I'm sure I've looked at this graph before and they told you the number of parts. Anyway, they've measured a whole bunch of production parts. So this is a 0.3 microvolt bin. So from there to there, so that's plus minus 0.15 microvolts. And you can see that, like 42% of them, of the parts, are going to be in that region. And some, like the production processes, they can drift like this. So this is not guaranteed. This is just what they measured. They will guarantee it's not more. They'll guarantee it's not outside of here and it's not outside of here. But, they're just showing you. And once again, this will be like a typical bell curve response, a parametric bell curve like that. So, they're finding that like most of them, it's like 70% plus of parts there are within like 0.45 microvolts, for example. So they're running a pretty tight ship here. So they say 2 microvolts maximum up here, but as you saw in the actual production test results, it's much tighter than that. But if you need to guarantee your performance for your product, for your customer, for your application, then you would work with the 2 microvolts, unless you want to bin them yourself. And you can do that. You can actually buy the parts and build up a custom test jig and actually measure it and then bin them good, bad. And you can do that actually on the component level or on the board level, because I designed a little amplifier board once that was used in a Sonoboy, and we actually designed this huge, like big, like table size automated, because we're manufacturing a couple of 100,000 of these boards, and we had to guarantee the performance of each one, fully characterize them with dynamic signal analyzers and everything, measuring all sorts of parameters and stuff like that. And we, it'd have like you'd load all the boards into a big like clip. You'd insert them all in, you put them in, and these automated actuators would shoot out the next board, and it'd travel along to a certain spot, and then a bed of nails probes would come down, and then it'd run the test, and then it'll lift up, and then shoot the board into a bin them, either a pass-fail thing or into a graded type thing. Anyway, what are we like 10-15 minutes into this, and we haven't even started looking for alternatives yet. Anyway, let's just say that we're looking for, in the order of, by the order of typically means like order of magnitude, but like we want to be a bit tighter than that. Not as tight as a nun's nasty, but we want to be reasonably tight. So, 0.1 microvolts-ish offset voltage is what we're shooting for. The 6.5 megahertz gain bandwidth product is what we're shooting for here. And everything like drift is, if you got a fantastic low offset op amp like this, the drift isn't going to matter. Noise, well, we'll look about that later. Let's just see if we can base it on those 2 parameters, offset voltage and bandwidth. All right, who's your favorite provider? Who's your daddy? Let's just go to Digikey first, shall we? Opamp, 46,000 op amps. Thank you very much. Now, of course, there are 2 ways to do this. One is through your component supplier's parametric search, your Digikeys, your mouses, your LCSCs, or your RS components, your Farnells, Element 14, whatever they call themselves these days, and all those parametric search engines. And they're not always infallible, but you can also go directly to the manufacturers as well. So I might have started this off by going to the Maxim website and using the Maxim parametric search, and we'll probably do that shortly. But for now, I don't care who my manufacturer is. You might have your preferred supplier, but I don't care. All I care about is that offset voltage. So here it is, chopper, zero drift, amplifier type. Well, you could say current sense. So I'm going to include, because that's our application, so I'm going to include current sense in there, just in case, because the art of parametric searching is to ensure you don't miss something, is to, try it many different ways on many different sites to make sure you don't miss anything, because there could be some obscure part somewhere that you're missing. And as always, there could be some obscure manufacturer I've never heard of. If you do know something better, of course, leave it down below. But anyway, instrumentation, no. Isolation, JFET limited, no. Programmable gain, nope. Transconductance, no. Variable gain video, no. Zero drift. There you go. It could have been classed as zero drift. See? Look, chopper, zero drift. and zero drift. Exactly the same thing, but two different, whoever was entering the data into this Digikey database, they went, oh, this one, they call it a chopper. And then they went, oh yeah, zero drift, but they didn't realize that they already had a category for zero drift. So there you go, trap for young players. We could have missed some valuable devices. I don't care about the number of circuits and everything else. I don't care about the gain bandwidth products. Let's just apply filter. Like we could have gone for broke right here and gone, oh, we only want the gain bandwidth product above blah. But anyway, I don't care. Let's go. 4,300. Whoa, this is heavy. All right, input offset voltage is the column that we want here. So let's sort from smallest upwards. Input offset voltage. Ta-da. Oh, we got some blankety blanks. Well, blankety blanks aren't going to help us, are they? That's really annoying. And these all happen to be the current sense amplifier type by the looks of it. No, it's 1-0 drift. Too bad if you use that microchip one. It's obsolete. Thank you very much. And dip package. That's probably why. It's probably still got the same chip. Now, I don't want to eliminate any of these, but for now, I just want to see what input micro... No, look. The lowest one we can get is the 0.1 microvolts. So let's just go, say we want, 250 nanovolts, something like that, okay? So there's 59 devices. They're mostly the same, but they'll just be all like different variants, stuff like that. Max 9922. There's a newbie. I don't recall that one before. Typical input offset voltage, 0.1 microvolts, but minus 3 dB bandwidth, 10 kilohertz. Well, that's not gain bandwidth product, is it? Gain bandwidth product is here, and it's got nothing in there. So I've never, once again, this is where you might find new parts. I don't think I've heard of the Max 9922 before, but anyway, let's go to the datasheet. All right, ultra precision high side current sense amplifier. It's a high side Jobby. We don't need a high side Jobby. I've gone into, in my power supply design thing, I've gone into high side design and stuff, for high side versus low side and things like that. Anyway, full scale gain, actually, plus minus 10 microvolts max. Oh no, that doesn't sound very good, does it? I'm not impressed by that. 0.1 typical plus minus 10. That's not nearly as tight as the 4239, is it? So I think you might be able to rule that one out here. Here we go. They got gain. Oh, no, that's gain history. Offset voltage. There you go. Oh, yeah, look, some of the bins are up in the microvolt range here. So, yeah, look at that too, So, yeah, it's just not as tight. Yeah. So, we'll go away from Maximum Renesas, ISL. Well, they've been buying. Zero drift, 3.5 meg gain bandwidth product. Not as good, but 0.2 microvolts, okay, I don't know, worth a squiz. Here we go, 5 volt, ultra low noise, auto zero, rail to rail precision, 2.5 microvolts max, so it looks like it's very similar, 3.5 meg gain bandwidth product. Is that similar to the 4238? So the 4239 still has the edge there. There's our VOS histogram. Fantastic. Number of amplifiers. There you go. They tell you there's sampled 1,400 amplifiers. Well, a couple of thousand amplifiers. That's each individual bin there. And each individual bin looks like it's 0.25 microvolts. So a bit tighter than the 4239. So that is an equivalent. I deem that to be an equivalent part apart from the gain bandwidth product there. So yeah, apart from that, without looking into further details, noise and drift and stuff like drift up here, we don't at 1 kilohertz, 1 hertz to 250 nanovolts. I can't remember what it was over there, but we're not too fussed about that. Common mode rejection ratio, 135. I think that's slightly better. Doesn't matter. We're not too concerned about that. 2.5 microvolts. That's pretty much the same as what we're getting. Is that's tighter over temperature, isn't it? So there you go. That's worth considering. And interestingly here you go. Let's have a look at the gain phase response, and you can see the switching frequency very similar. That's that little dip in there like that. So the switching frequency round about 15 kilohertz, very similar to the Max 4239, and you can potentially come a gutser with that. You've got to be careful if you're actually using it at that specific frequency. The amplifiers can, start to do some wobbly business, and you can come a gutser but it's got to be at the specific frequency, which is not tight, by the way. It drifts with temperature and all sorts of things. That's why, they probably won't even tell you the switching frequency apart from nominally 15 kilohertz or something like that. So it's rail-to-rail input, of course. We don't need a rail-to-rail input because we're measuring just from unless you had a single supply and you wanted to measure right to ground. But rail-to-rail input is not necessarily ground sensing. So just be, they can be different things. So you can come a gutser there. But anyway, the rail-to-rail input and output, that's quite nice. So yeah, that's not a bad part. And that's been updated March 12th, 2020. So that's updated. Is this a new part? I don't actually recall it before, but yeah, it's they've got a spice model as well. Competitor A. Oh, come on. Tell us. Put the part numbers in here. Come on, man up. Tell us. Oh, they got a spice schematic as well. Wow, go Renesas for the win. Wow, you spice aficionados getting all moist right about now. Oh no, it's an old part. 2011, there you go. It's old as the hills. Aha, looks like they've updated all the stuff. Is that when have Renesas just recently bought? Sure enough, Renesas acquired Intercell, which is the ISL partner, the ISL designator on the front of that. That was back in 2017. I don't know, I might have covered that on the amp hour. So many companies being bought it. We gave up trying to keep up with who's buying who in the electronics business. It was just insane. So yeah, okay, that one's all right, but it's not significantly better. So, I'm not going to be writing home to my mum about that one. I'm looking for something better. And right off the bat here, just on the input offset voltage, nothing is showing up here. It's the maximum 90, well, where's the 4238, 4239? Why is that not right up there? Aha, now get on to page 3 here, and TI OPA 2388. It kind of rings a bell. We're talking 0.25 microvolts, 10 megahertz gain bandwidth product. So that's definitely worth a squiz. Beware sneaky buggers that try to put, instead of nanovolts per degree C drift, they put it microvolts. Why? Is because 0.005 registers in your brain instantly as better than 0.5 nanovolts, or 5 nanovolts per degree C. Little marketing trick there. Yeah, good on you, TI wankers. 140 CMRR, true rail to rail, low noise, 7 nanovolts per root hertz at 1 kilohertz, 1 on F from 0.1 to 10 hertz. I think they're all the same. Anyway, gain bandwidth product, 10 megahertz, single supply, same as the 4239, true rail to rail input and output, EMI RFI filtered inputs. That's nice. Current shunt measurement. Geez, that's just what we want. Ultra low noise, fast settling, zero drift, blah, 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 blah. 0.25 microvolts, plus minus 5 microvolts. So, you got it's not as good. The max 4239 is still better. Because once again, if we had that, and it was typically around that, and we used it with a 4.5 digit meter, you'd get plus minus 2.5 least significance digits flapping around in the breeze. Well, they're not flapping around in the breeze. They'd be, you could null it out. But anyway, we're after a precision op amp. So not quite as good. But if bandwidth mattered, if that could give you some benefit over somebody else's product or something like that, then you might go, hey, I'll sacrifice some of that offset goodness for bandwidth. Oh, wow, the input offset voltage distribution here, that's wide as the Harbour Bridge. That's a bit how you doing. Yeah, that's not quite as good, is it? Not quite as sharp. So much larger specification there. And offset voltage drift, we don't really care about that. But yeah, not as good as the Maxim. So really, out of all those, that's all we had was 3 pages. Pretty much only 3 major parts there, and really nothing better than the max 4239. But why isn't the max 4239 there? That's interesting. Search for Max 4239. It's there. What's uncategorized? One new product. What's that? Ooh. Marketplace product. Unable to receive pricing or stock at this time. What's a marketplace product? I haven't seen it. Online and Digikey Marketplace provides access to a broader range of suppliers and products. Uh-oh. Ding-a-ling, ding-a-ling. Warning, Will Robertson, warning. Yeah, where are they getting it from? Whoever they can find at the Shenzhen market this week. Marketplace products shipped directly from their supplier. Yeah, from their supplier. Who? From under the table in the Shenzhen market, in a stall at the Shenzhen market, and may incur a separate shipping fee. Service typically available, may not be available. Yeah, you would not be touching any sort of product that didn't come from direct from the manufacturer. So you can really come in as a supplier. There you go, it comes from, and then they tell you, Rochester Electronics. Wow, I didn't know Digikey could actually source them, but they're out of stock, but presumably they can source them from other suppliers. That's interesting. Is that new? I hadn't seen that. Maybe it's been there for a while, but yeah, buyer beware. Yeah, there it is. The Max 4239 AUT and all those letters after the name, like the plus means it's ROS compliant and stuff like that. And anyway, let's 0.1 microvolts. So yeah, why didn't that show up on a general search for low input offset voltage op amps? This might be a good example where you could actually come a gutser doing this. So let's actually go back. And the good thing about this is you can go back in your parametric searches like this, and there you go, input offset 0.1 microvolts. Like, why doesn't the 4239 show up in the 0.1 microvolt input offset? That's interesting. So if we clear that and we just apply filter, now I think we need to go back a bit. Maybe it wasn't under the amplifier type here. I think it might have been categorized as a different amplifier type. So let's go back here. Okay, let's go. We could just clear all selections, right? And but here's where we selected these. Let's actually clear those selections. Okay, let's get rid of those, and let's just now go apply filter. And how many responses? 46,000 results, but that's okay. We can go input offset voltage, go from NAF all, right? And then choose, because it might have been under like general purpose. I think it was under general purpose. Aha, see, we've come a gutser already. So yeah, don't follow dumbass Dave. I guarantee you, that's the problem. You search for input offset voltage like that, and you search for filters, and you search for 0.1 to 0.25 microvolts like we did before, but we don't have a category selected, then bingo. Oh, 4288. What's the 40? Obsolete. IC buffer. That's interesting. Anyway, 4238. There it is, 4239. We found it because it's under general purpose op amps. Yeah, there it is, general purpose. So yeah, we come a guts are doing that. Anyway, so this has given us another, but once again, there's nothing better, like we showed here, there's nothing better than 0.1 microvolts. So really, yeah, nothing better exists. Searching every single op amp on Digikey, nothing's better than 0.1 microvolts. Just not going to get it. But we might get something, say, let's just go, say, for that, and go for the gain bandwidth product. Well, let's apply filter for that, and then we'll filter for gain bandwidth product. Where is it? Is it no, there it is, 10 megahertz. 10 megahertz is the best. We'll get that TI. These two here, ones, will get that TI part and the Maxim parts if we select those. And bingo, 4239, and the Texas Instruments part down there. That's it. It's nothing better. Does that end a video? Right, so what we can do is just go to TIcom here and go to their parametric search products. Haven't done it in a while at TI. Where is it? Let's go into amplifiers, featured products. Once again, you can do parametric cross-reference here. Search any supplier's op amps to find similar devices by part number. Let's actually try that. Let's put it in the Max 42. Can we, other part number, Max 4239. Can we do that? Select. VOS, there you go, 2 microvolts, 5 microvolts. Okay, oh, 1 microvolt. Hang on, what's the TLC 2652? Precision chop and stabilized operational amplifier. That one didn't show up in our Digikey search, did it? That'll do plus minus 5 volts too. So there you go. If you wanted to needed a larger dynamic range, that might be better than the other alternatives. Datasheet's the easiest way to see it. 1 microvolt max. See, technically that is better than the 4239, 1 microvolts max. Whereas it's 2 microvolts max on the 4239. And right up the top, here you go. We've got our distribution. No, see, they're down, like, a good lot of them. Like, some are down at the -1 microvolt level. So that's not terrific. Compare that to our 4239 over here. Oh, look, you know, good bulk of them. That's tighter. That's tighter. So yeah, they might claim a lower max, but in practice, you might find that the 4239 is still better. Once again, not going to write home to my mum about this and say, oh, this is 1 microvolt, and therefore it's better than the 4239, but look at the spread. I mean, the spread on the high side here is, but that's just how they happen to test it on that day, you know. So anyway, no. So, you know, it's probably a reasonable alternative part, especially if you needed that higher voltage rail and better dynamic. Oh, die shot. Thank you very much. It's, you know, it's bonding because you can probably buy it as a bare die and then bond it yourself. For hybrids and stuff like that, it's very important to be able to, pretty much any manufacturer, if you go to them and say, we need a bare die version, they will send you copyright 1988. That's ancient. Wow. Anyway, that's been around for a while, that Jobby. Anyway, they'll sell you bare die for a price, even if they don't have it in their as their standard ordering thing. I'm sure they will do it. They'll bend over backwards for you. Anyway, let's go into precision op amps here. 343 different op amps. That'd be all parametric difference. Low offset, less than 500 microvolts. This isn't necessarily the proper parametric search, but I'm just going into, zero, no, I saw it, zero drift, go back, zero drift, less than 20. So low offset, find products. We are in our parametric search here, but once again, they could miscategorize them, but that's extremely rare for that to happen on a manufacturer's website. You'll get that on the catalog suppliers' websites, but not on the manufacturers. So yeah, that's fine. So we should be able to search, sort, not gain bandwidth product, VOS. There you go. Hang on, that's 0.5 millivolts. No, we're after microvolts, so we're in the wrong category. Current sense amplifiers, because that's exactly what we're doing. We're doing a current sense, so they're going to be optimized for low offset voltage. But some of these are obviously, look, you know, high voltage, you know, 40 volts, 110 volts, you know, high side current sensing and stuff like that. So not necessarily the best thing. Can we just go to operational amplifier and where's the parametric search for just all op amps? I want to search every single op amp, 1,520 of them. Search all precision op amps. Offset voltage, millivolts. Did I have that around the wrong way before? I might have been sorting that the wrong way. Chopper stabilized. 0.0. Anyway, 1 microvolt Jobby. There you go, the TLC 2652. Already looked at that. The OPA 189. Oh, look, 14 megahertz. MUX friendly. Wonder what makes it MUX friendly. That'd have to be some dynamic switching performance thing, surely. And the 2652, they actually list that differently to the 2652A up here, because the A version is just tighter tolerance. Yeah, that one's tight as a nun's nasty. This one's a bit loosey-goosey. Anyway, the 189, I think I remember that. I think that's been around the traps for a while. 3 microvolts maximum guaranteed. That's okay. There it is, robust, MUX-friendly inputs, RFEMI. That'd be for transient switching on the input, so that it didn't, so it's probably got fast settling, probably got fast recovery from input. That could be handy in your design. They've obviously had like some customers with that problem actually request, or, you know, that sort of thing. So Yeah, robust mux-friendly input, inputs without anti-parallel diodes. There you go. So anti-parallel diodes, I want to find settles quickly and maintains high input impedance when switched. That could be handy for something like what we're doing with the µCurrent, for example, especially like an auto ranging type version. You don't want them to be overload, because overload recovery time, have I done a video on overload recovery time? I'm sure I have somewhere. Rings a bell. I've done like 1,500 videos or something. Can't remember. Anyway, yeah, recovery time can be a big thing when you overload the op amp. You go full scale input and the output clamps hard. It actually takes time to recover, and then you can actually lose data in there when you're like trying to sample what's actually happening, because it takes a certain amount of time to settle back down. So yeah, that could be a big thing. Competitor high voltage amp. Mux friendly prevents loading of source. Oh, that prevents, oh, okay. Okay, so what they're doing, no, it's got nothing to do with the settling. It's the loading of the source, hence why they don't have the anti-parallel diodes. Because when you got a mux, got to remember, a mux is just basically a resistor in series with it, and like a selectable MOSFET which has a series resistance, effectively series impedance, and then it switches it through, so it can load down. If you have these anti-parallel diodes, when you're switching, it can actually load down your loads and stuff like that. So yeah, okay. See, now this is kind of an example of where, even though we're still searching within op amps, you might find an obscure device like this and go, oh yeah, I had this other design I was thinking about, but Kamagutsa, when I was switching mux, this has got mux friendly inputs. So, you lock that away mentally up here and go, oh yeah, I've heard of that. When another design application comes along, oh yeah, these mux friendly input ones, I remember those. 0.4 microvolts of offset voltage, if that's their banner spec, then, it's not as good as the 4239. Plus minus 0.4, plus minus 3 microvolts max, yeah, it's not as good. So unless you wanted the gain bandwidth, the increased gain bandwidth product, the common mode rejection ratio, that's not too shabby, is it? Plus minus 18 volts. Wow. If you wanted your headroom, wow, really? Yeah, 4.5 volts to 36 volts. Wow. If you wanted your dynamic range, this Jobby's got you covered. Wow, okay. That's impressive. Imagine having plus minus 15 volts of dynamic range. Whoa. So yeah, mental note on that one. Mux friendly and a huge supply voltage range up to 36 volts. Not necessarily what I'm looking for, and a 14 megahertz gain bandwidth product. Wow. How much is that, Jobby? OPA 189. Geez, that's all right. $2.50 for one-off. $1.12 in 2,500 real quantity. That's pretty good. Okay, let's go to analog devices here. Amplifiers, RS specialty amplifiers. Boop, boop, boop. Precision op amps, VOS, less than 1 millivolt. Yep, that's what we're... Zero drift. No, we don't want a zero drifter. Zero drift, there we go. Zero drift op amps, combine auto, zero, and chopping techniques to continually was identified less than 0.4 less than 4 microvolts. So it looks like analog devices and 2 microamps. Oh, they've got a 36 volt Jobby too. Whoa. To chop or zero? That is the question. So there you go. You come across interesting articles like this because a chopper amplifier is better at like lower frequencies and stuff like this, and auto zero techniques. And here's some of the auto zero techniques. I'm sure I've gone over these before, and how they switch the thing in, and they constantly, basically basic topology is they're constantly correcting for the input offset voltage. So that's what they do. So yeah, chopping technique. Oh, there you go. It's a bit complicated there, but and combining auto zero with chopping, there you go. So that's kind of what they're doing. All these different phases inside the op amp. So that's what's chopper stabilized. And so there you go. Different auto zero uses sampling to correct offset, whereas chopping uses modulation and demodulation. Sampling causes noise to fold back into the baseband, and you don't want that. You can Kamagutsa auto zero have more in-band noise to suppress noise, blah blah blah. And yeah, pros and cons both ways, application suggestions and things like that. So that's a nice little article. you know. Okay, parametric search, VOS, sort, 2.5 micro, ADA 4528. Oh, they got high voltage parts and things like that. That's quite neat. High voltage working with a strain gauge. Anyway, it looks like the best they got here is, where's gain bandwidth product, 3.4 meg, 2.5 mic. I don't even need to check it. It's not really happening. It's not blowing my socks off. The 4230 max 4239 is 6.5 meg gain bandwidth product. Nothing's, you know, they've got nothing there that stands out. So yeah, no. TI, nope. Analog devices, nope. I mean, we can look at more. I mean, mouse is going to have the same thing. I greatly doubt that mouse is going to have anything else. Operational amplifiers, input offset voltage. That's no good. One microvolt. Oh, here we go. Okay. Apply filter. And on semi. That's national semiconductor part number. But here you go. We've got an interesting one down here. This is where, you know, you find this interesting stuff. I don't know why they've only got 3 here. I've goofed. Amplifier ICs, operational amplifiers, VOS input offset voltage, multiple values. Okay, so maybe they didn't have all the data. Maybe it's not as good as Digikey. Anyway, we found a manufacturer who is Ablic. I've never heard of Ablic, but they make zero drift op amps. So I'm going to give them a go. Let's have a squiz. Who is Ablic? It's ablic.com. This is one of the fascinating parts about looking for stuff. World's thinnest Hall effect IC, create comfortable. What do they make? They make real-time, wake-up, interval counter ICs, power sequences, wireless power ICs, E2 prom, power management ICs. Okay. They probably don't mine be a Mitsumi. Minbia Mitsumi. What? Who are they? Ablic? Who or what is that? Sorry, it isn't an ad. Like, is it a parent? Is it a company? Begins selling masks on Amazon. What? What? Selling masks? What? Oh god, it's an ad. I've been mask rickrolled, I think. The world's lowest self-current consumption. Industry's fastest detection. Whoa, I missed it. Often these banners up the top, you know, they can highlight new products and stuff like that. Worth squeezing through them. Industry's fastest detection of voltage malfunctions. Really? Wow, there you go. I guess in self-driving cars, that's important. You know, these days, true autonomous cars. Decades away. It's like nuclear fusion, 20 years away. Yeah. Antenna diagnosis ICs. Wow, composite ICs. Lithium-ion battery protection. Oh, they do. Wow, they do a whole bunch of stuff. But look, operational amplifiers, ultrasound, transmit pulse, and digital transmit pulses. Wow, look at that. That's relevant to what we've done recently. Ablic quad octal 16 channel pulses, integrate logic and MOSFETs and stuff like that. Oh wow, there you go. They make specific ultrasound. If you wanted to know who make these ultrasound switching front ends that could be used in, you know, the new Philips ultrasound probe that I've looked at in a recent video. I looked at an old one, but they've got new ones. Then yeah, there you go. Ablic, and they make operational amplifiers. Let's go and have a squiz. Just for kick. Oh, yeah, is that it? Yep, they got 3 parts. Automotive zero drift operational amplifiers supporting AEC Q100. Don't know what that is. Obviously some standard. Is a failure mechanism-based stress test qualification for packaged integrated circuits used in automotive applications. Okay, so it's an automotive application qualification for RF immunity, basically, I think. That seems to be what it is. Devices pass the specified stress test guaranteeing a certain level of quality and reliability, grade 0, blah, blah, blah. Anyway, so you can find interesting stuff like this that you didn't know about before. Yeah, we're only talking input offset here, only talking 50 microvolts here. So, yeah, it's not it's not that great. But, Rev 1.100. Yeah, 50 microvolts max, you know, so we're not even in the ballpark. But there you go. Interesting, because these will be automotive. Oh, gee, what's the collective term for diodes? They're really gone to town. There you go. So yeah, they've got the anti-reverse parallel ones. They're they're anti-mux. You remember that? So yeah, so we've got just protection everywhere. So we've got one diode right across VDD and VSS, right across, and the inputs and outputs, and geez, yep, they're really going to, and they're probably beefy too. Being, you know, automotive type thing, they really want to clamp that protection. So anyway, yeah, that's not going to set the world on fire, but hey, you know, automotive jobby. So anyway, I don't know what's up with Mouser here. I've obviously done something dumb, haven't I? Oh no, why didn't I see this category 0.25 microvolts before? 0.1 microvolts is down. No, they might have. Be careful, you can come a gutser here. Oh, come a gutser, they might categorize these things wrong. Or they might have no category entry whatsoever and you could miss it. I don't think we're going to see anything here that we haven't seen before. Oh, linear tech, 2064. Input offset voltage 1 microvolt. No, I don't. Oh, well, no, okay. Let's go have a look at that. Okay, 5 microvolts maximum. Okay, so it's not going to be as good. Let's go down to our parametric spread. Duty cycle lower system power. Input offset voltage, typically 1 plus minus 5. Once again, yeah, it's not as good. What's our gain bandwidth product? It's not here. It's gain bandwidth product, 20 kilohertz. Okay, yeah, no, it's not even in the ballpark, is it? And there's our distribution, 233 typical units. Well, don't overdo it there. And then, no, look, plus minus 2. Nah. So it looks like that's basically it. I don't think that we can beat the 4238, 4239. You know, I could spend another hour or two doing this, but for the purposes of this video, I think we're gone far enough. Please, if you know of a better part than the 4239 for typical offset voltage, a typical and max offset voltage and gain or gain bandwidth product, please leave it in the comments down below. I do read all comments, or I try to, especially in the hours and the days after the video is released. But yeah, I do try to read all the comments, and I try to, you know, and I heart them, and I thumbs them up, and I do all sorts of, you know, and I pin them and all that sort of jazz. Anyway, yeah, if you know of a better op-amp, please lift it, but please list it down below. But it looks like, you know, just off the bat here, the Max 4238, 4239 is still pretty much the duck's guts for this sort of application. So, yeah, there you go. Nothing's changed in, like, you know, 12 years at least. So that's interesting. Anyway, video's waffled on long enough. Hope you found that interesting. If you did, please give it a big thumbs up. Yeah, I've said comment down below, and over on the EEVblog forum, that's where everyone chats about this sort of stuff. And yeah, I'm on all the platforms, the libraries and the BitChutes and the Vimeos even, and the all sorts of stuff. So yeah, hope you found that interesting and useful. Catch you next time.